Good afternoon, everyone. I, Harshit Singh Rajawat, your today's host. Good afternoon, everyone. I, Harshit Singh Rajawat, your today's host, welcome each and everyone present here for today's session. Before starting the today's session, I request the FTP coordinators to present a bouquet to our resource person, Dr. S.K. Masiul Islam, Senior Scientist, Siri. Now let me quickly introduce our resource person for today to everyone. Dr. S.K. Masiul Islam joined as a scientist at CSIR Siri in 2016. Currently he is working on semiconductor sensors and microsystem groups at CSIR Siri Pilani as a senior scientist. He is also an assistant professor in ACSIR India. He has completed his PhD from IIT Kharagpur. He is currently researching on third and fifth semiconductors, graphene-based flexible electronics, thin film solar cells and nanobiosensors. Dr. Islam has published over 35 research articles in peer-reviewed journals with international reputees as well as presented paper in national and international conferences. Now I request Dr. Islam to address the gathering.
Now it is audible. Right? So, very good afternoon, all of you, on and all present here. Now, title of my topic is today's presentation: MOCVD on indium arsenide. That is basically belongs to 3-5 classification in the periodic table. Quantum dots in gallium arsenide MOS. MOS means metal oxide semiconductor, and graphene based devices for electronic application. Basically, I have divided this title in two parts. One is gallium arsenide MOS, and another thing is graphene electronics. And basically, gallium arsenide MOS I have undertaken as a part of my PhD curriculum at IIT Kharagpur, and graphene electronics, graphene based devices I am currently undertaking at CSR CD Pelani through my project. Next. Now, first of all, queries comes into my mind: why people are so much interested in case of 3-5 materials. 3 means, okay, you see in the periodic table group 3 and group 5. Okay, 3-5. Why 3-5? Gallium arsenide belongs to gallium belongs to 3 and arsenic belongs to 5, because of its very attractive property. What is that property? These are this property. It is the comparatively stable material in comparison to the other materials. Now you can see, as you can see here, your band gap also varies with a wide range, as well as band gap engine. You can also tune the band gap of the material by suitable alloy formation. You see here in the diagram, it also exhibits better emission and absorption efficiency. Okay, now in case of this material, 3-5 material, it is possible to growth on a desired substrate in a very controlled manner. Now, since initially I have told that it is a gallium arsenide MOS, means metal, then oxide layer, then gallium arsenide. Metal, oxide, then third layer is your gallium arsenide. Okay. People have used it as a channel material. Why it is used as a channel material? because of this extraordinary property. What is that property? It exhibits high electron mobility. You know, at least 5 times greater than your silicon. In case of gallium, your electron mobility 8500 centimeters square per volt second, and in case of silicon it is 1800, at least 5 times greater than silicon. And is high breakdown field. It also exhibits high breakdown field, low power consumption, high speed application. That's why it also facilitated application in high frequency devices. Okay, these facilities favors gallium arsenide for suitable application as a channel material. Next. Now there is certain limitations of using gallium arsenide. Gallium arsenide. You see, like silicon SiO2 on silicon. This SiO2 is very stable native oxide on silicon, but unlike SiO2 on Si, it does not contain any stable native oxide. You see, gallium oxide, other formation is also there, Ga2O3, Ga2O5, and arsenic oxide is also there. That is not very stable. That's why your if you form the interface, gallium arsenide and other material, that interface exhibits so many interface trap charge density. That interface trap charge density is responsible to degrade your device performance. And because of this interface trap charge density, you see, if you draw the band diagram, your Fermi level is there. Your Fermi level is pinned near the interface of this high K dielectric or any material and between and the semiconductor, right? That's why prior to the deposition of any layer, prior to deposition of any layer on gallium arsenide surface, you have to passivate the gallium arsenide surface with a suitable layer. And in my case, I will show you in the later slide, I have used ultra thin passivation layer of gallium phosphide. Next. Again see, initially I told that it is a MOS devices. MOS means metal, oxide and semiconductor. Semiconductor metal, you know, that is the gallium arsenide, and oxide material I have used here zirconia. Why very high K? Zirconia is very high K dielectric material. Why high K is needed? You see, C equals to E0 by T of oxide thickness, that is your dielectric constant K, and this is relative permittivity in free space. Okay, and if you see here, COX directly proportional to your K by TOX. See, you have to increase the capacitance. If you increase the capacitance, what is the option? You have to either reduce your denominator, means the T oxide reduce, or you have to use K value very high. Okay, but you cannot reduce the thickness of the oxide very thin. Okay, if you take very thin material, in that case your leakage current density will be very high. That is undesirable. That's why only option is your K. If you take the material with very high K dielectric constant, in that case your capacitance will be higher, because your target is to get the high capacitance, because it is a gallium arsenide based MOS capacitor. Okay, now your option is K. So now in case of SiO2 also there is limitations is there. In that case SiO2 also, that's why we are not using in this case SiO2, because in that case very high leakage current density is there, and that will device will break down in a certain extent. That's why high K dielectric constant, use of high K dielectric is essential requirement for this fabrication of your MOS capacitor. Next. Now as I told that you have to use very high K dielectric material. Okay, you see this picture, this diagram, you cannot use very high K dielectric material, very high K. You see, if you want 10, 100, 10,000, if your dielectric constant get increases, in that case your breakdown field also decreases. That's why you cannot choose a material which also have very high K dielectric material. In that case, what is the option? You have to make the trade-off, so that it can effectively balance both the needs. One is dielectric constant, another one is your breakdown field. See, if you increase your dielectric constant, in that case your breakdown field also decreases. That's why I have chosen in my work ZRO2. You see, dielectric constant is your 25 and breakdown field is your near about 3.8. Next. Now advantage of MOCVD. Again question arises, what is MOCVD? Metal Organic Chemical Vapor Deposition Technique. It is a basically technique. Technique of what? Technique of depositing some material onto that material. Okay? Some technique, CVD, chemical vapor deposition. Some chemical species is there. That chemical species will go to the transported to the reaction chamber, and there already substrate is there, and chemical reaction will take place, and your desired material will be deposited on that substrate. In this, what is the advantage of MOCVD? You see, in very industrial application, in all industry, people are now using MOCVD technique rather than your MBE. Why? Because it has certain advantage. What is that advantage? It does not require any ultra high vacuum that is needed in case of MBE, molecular beam epitaxy. And here you can also grow the material even in the atmospheric pressure, and in that case is also facilitate very large area coverage. You can be 5 by 5 inch, 3 by 3 inch, the growth is possible, and it is also control various thermodynamic reaction as well. Next. Now you see these are the reaction steps basically using in MOCVD. You see what I have used here. I told you in the title I have used gallium arsenide MOS, and in that gallium arsenide MOS what I have used indium arsenide quantum dot. Why? Because this indium quantum dot will act as a charge storing element. Capacitor means is what? That is actually store the charges. So who will store the charges? That is indium arsenide quantum dot. When you are going to bulk to nano, okay, then rather than your continuous various discrete energy levels will be created. That discrete energy will be created in case of indium arsenide quantum dot. Later I will show you. Okay, and that discrete energy levels will store the so many, that is the energy level will is responsible to store the charges. Now you see what is the reaction step. First of all the reactant species. What is that species? I told you MO means metal organic. Why metal organic? This you see pointer is not there. No. Go to previous slide. Last equation you see CH3 whole 3 ion plus ACH3, that is arsine. Okay, because I need indium arsenide. That's why CH3 whole 3 that is your organic compound, indium is metal. I show you metal organic because this species contain both metal and as well as your organic. That's why metal organic. So because I need indium arsenide, that's why you have to take CH3 whole 3 in trimethyl indium plus arsine equals to indium arsenide plus CH4 methane. Methane will go as a used as a byproduct that will vent out through the scrubber system. If you see here I have used indium arsenide. Let's see if one use gallium arsenide. So then in that case what we will have to use? Trimethyl gallium, CH3 whole 3 Ga plus arsine, then your gallium arsenide plus that one. Suppose you want to gallium phosphide, then what should you use? CH3 whole 3 gallium plus PH3 phosphine. If someone wants to, then what will get? GAP gallium phosphide plus methane. So that's why you see that compound, your trimethyl indium and arsine together will go to the reaction chamber. You see 1, 2, 3. That is the gas stream that will carried out by your carrier gas. That is, in my case I have used hydrogen, and that reactant species will go to the reaction chamber. There all the reaction, that is decomposition, surface migration and site incorporation will take place, and finally your desired material, that is indium arsenide, will be deposited into the substrate material. And this is the methane is your byproduct. That methane is undesirable. That will be number 7. That will be vent out through your scrubber system. Next. Now growth of indium arsenide. Now basically if you see the quantum mechanics epitaxial thin film deposition technique, there are so many deposition techniques are there. One is Volmer-Weber growth technique, and second one is Stransky-Kastonov growth mode. Here I have used actually Stransky-Kastonov growth mode because you see in this growth mode what happens, basically at a certain critical thickness initially 2D thin films are happening, but that 2D thin film actually situated in a very highly strained condition, but every system wants to release energy, was because of minimization of surface energy that deposited 2D thin film will relaxes into the 3D islands. So initially what happens, initially thin film will be formed. That thin film, because of the surface minimization, will be then formed into the 3D islands. Next. Now limitations of high temperature growth, that is actually literature survey. If you see in the literature, people are using indium arsenide quantum dot rather than your metallic nanoparticle, and in all the cases people have used your very high temperature growth more than 500 degrees centigrade. But in my case I have limited my growth rate from 380 to 500 degree, because if you increase the temperature, in that case your quantum confinement effect will be lost, your site will be gauged bigger if you increase the temperature. Again, thermal out division will be takes place, and your crystal quality will be get degraded, and sometimes it may dope the material, and eventually what happens, gradually charge loss is happening from the program state, and this will finally greatly degrade your charge retention characteristics for memory application. Next. Now, as I just said earlier, that instead of using quantum dot, previously reported also there in the literature available, people are using metallic nanoparticle, but instead of using metallic nanoparticle, I have replaced that metallic nanoparticle with indium arsenide quantum dot. Why? Because if we use the metallic nanoparticle, then see, metal oxide, in that case your metal may react with the oxide material. Sometimes we could have temperature processing, it may dope the material even it is source and drain region. Okay, again the synthesis of metal nanoparticle is a very critical task. Now again you see, you can see there in the next slide I have schematically shown there, it does not finds in conformality to the present process lines of the device manufacturing technology, because all the layer which I will be shown you in the next slide, all the layer will be deposited through the your epitaxy. Next. Now motivation of the investigation, use your replacing your metallic nanoparticle. In this case I have used indium arsenide quantum dot as a semiconductor, and as well as your growth temperature will be quite lower below the 500 degree centigrade, because again here you see quantum dots basically. Why quantum term I may used? Because you see what is quantum. In this case you have to realize that the size of the particle, when you are go from bulk to nano, size of the particle will be at least comparable to your excitonic bore radius or de Broglie wavelength, right? In this case I will calculation is there, I will show you. Now quantum dot also favor low leakage, because discrete energy levels is there, that will responsible to store the charges. Low voltage operation, low power consumption will be received, and it is generally considered that epitaxially grown quantum dots are considered to be very less defect. Next. Now this is the another study, MOCVD growth and characterization of indium acid quantum dot or p-type gallium acid substrate, and as well as on the high K dielectric. So what you see, this is the next. So this is the parameter I have used. Growth temperature is your 380 to 530 degree centigrade, and growth duration is 3 minutes and 5 minutes. This is actually MOCVD system. You see, that is actually your reaction chamber. All the precursor molecule will be controlled through this monitor, and another your valve is there that will passes through this reaction chamber, and there actually reaction will takes place. Next. This is another system I have taken from the literature. In series, this one is there, and previous one I have used at IIT Kharagpur. This in series, this Thomas one system is there. You see here the tungsten heater is there, heater coil, and another 4-inch wafer, 5-inch wafer you can use. Next. Now, for in case of our, I already shown you, because our desired material is indium arsenide. That's why you see trimethyl indium, your flow rate is this one, arsine flow rate is 75 SCCM, and hydrogen your 4 SLM or 4000 SCCM. Next. You see, this is the actually atomic flow microscopy images. This is the grown indium acid quantum dot on gallium arsenide substrate. Your substrate is gallium arsenide. Upon that, I have deposited gallium. You see, this is 380 degree. Again, your temperature is increasing. That is 400 degree centigrade for 30 minutes growth. That is your C 400 degree centigrade for 5 minutes. D 450 degree for 3 minutes and 530 degree. You see, if you increase the temperature, you have seen there, your size of the particle will be very prominent. Why? I will explain you in the next slide. Next. And this is the your TEM images, transmission electron microscopy images. You can see your black spot pattern clearly indicates your formation of your dots actually. Next. Now this is the calculation of excitonic bore radius. How you can say that that is actually quantum dot is from? You see, exciton bore radius can be calculated from that equation. All the terminology is there. Okay, if you put the value, it will show what the amount is, that is your 36 nanometer. So in case of indium arsenide, your particle size is excitonic bore radius is 36 nanometer. So we can consider indium arsenide as a quantum dot or bulk material if your size of the indium arsenide below 36. So if you get obtain your indium arsenide quantum dot below 36 nanometer, then you can see that your actual particle is in quantum state. Next, you see here, this is the growth temperature, this is your E. You can see at 380 degree centigrade, you can see 380 degree centigrade, your particle size and diameter in your height will be below 36 nanometer. Okay, and if you and another important significant is that if you increase the temperature, your size of the particle gets increases while your density decreases, because if you increase the temperature, your precursor molecule that I use, trimethyl indium and arsine, that adatoms becomes more mobile. If you increase the temperature, that adatoms molecule becomes more mobile, and that will facilitate very high thermodynamic action. So rather than formation of your quantum dot, that will actually thin film will be deposited. That's why formation of nano island will be formed. Okay, so instead of formation of quantum dot. Next, and this is your AFM images on tunneling zirconium oxide. You see, because this is actually growth study. Previously it was on gallium arsenide, and it is on, that is on dielectric actually, tunneling ZrO2. So this is actually 500 degree centigrade, this one 550 degree, and later one is 580 degree centigrade. In all the cases, if you see, this is actually in the range of 5 nanometer, that is 12.5, and that is 16 nanometer. Next, and this is the corresponding your TEM images of that material which I have shown previously on ZrO2 substrate. You see your quantum dot is that black spot pattern confirms your formation of quantum dot in all the cases. First one is your 500 degree. To ensure the formation of quantum dot, I have experiment both. One is your AFM, another one is transmission electron microscopy. Okay, and the number D is your HRTM image. You can see the crystal lattice also. You can see the lattice fringes is there, parallel lines. Okay, next. Now, another important question you may ask me, when I did the material characterization with AFM, then your size is, indium size is quite bigger. But when I did your transmission electron microscopy, your size is quite lower. Okay, why? In case of AFM, you see, this is the actually AFM tip. When you scan the surface, suppose you are scanning this surface, then tip actually, suppose this is round shape, so your tip is cannot penetrate this region. It will raster scan through this one. That's why in case of AFM, actual size will be this one. Okay, so instead of traveling this one, because this tip cannot penetrate this region, cannot travel, it will travel through this. Okay, that's why in case of AFM, your particle size is quite higher, and in case of your transmission electron microscopy images, your particle size will be quite less. But it can be means adjust by your tip size convolution effect. इसको नेक्स्ट कैसे करेंगे? आ गया ना? हाँ हाँ ओके ठीक है ठीक हाँ ओके. Now you see, this is a set your what is selected area electron diffraction pattern. Okay, this selected area, why this is needed? This is actually confirms your single crystalline or polycrystalline nature. Okay, you see this bright spot pattern actually confirms the formation of single crystalline in nature, and the lattice spacing is your gate is 2.94 angstrom. Next. Now, in order to confirm the formation of indium arsenide in both the cases, okay, this is the actually chemical analysis. In order to ensure whether indium arsenide is formed or another material is formed, you have to ensure that this is actually X-ray spectra, X-ray photoelectron spectroscopy. You see indium 3D 5/2, this peak 440.3, and in here your orbital splitting is takes place instead of 3.2 and 3. These two distinct peaks are arised. So this peak is corresponding to indium 3D 3/2, and 443 is responsible for indium 3D 5/2. So this will confirm that your material is in terms of indium, nothing else. Again, for that material we have used this one for arsenic. You see, suppose in, this peak is responsible for arsenic and indium. okay, 41 per proton electron volt, and you see the intensity of this peak oxidized state is very low. So rather than formation of oxide, your this material is formed. This again ensure the chemical composition of indium arsenide, nothing else. Next. Again, I have also undertaken the material ZrO2 material for chemical analysis. This is again your photoelectron spectra of ZrO2. You see, in this case, Zr3d 5 by 2 and Zr3b 3 by 2. Both peaks are very distinct peaks corresponding to 185.1 electron volt. This is responsible for Zr3 by 2. And why this peak arises? This, if you see the chart, actually 180.28 will be responsible for your Zr3d orbital splitting. Actually, this is 5 by 2. So here you can confirm the material is your zirconia. And oxygen 1s orbital, you see this peak arises very broad, very sharp peak is there, 530.1 electron volt is responsible for your oxygen 1s orbital. So for these two in combination, you can confirm that, ensure that your material is ZrO2. Next. Next. Now for the fabrication of device, this is actually related to your material processing. How you have fabricated a device. I have told you that is actually metal oxide and gallium arsenide. First of all, prior to the fabrication of device, we have to clean the surface of the gallium arsenide. I told you so many interface trap charge density there, so it will be degreased through acetone, methanol. I think you know this, and this is your base Pirana solution. You have to dip it into 1:1:2 solution into this solution to remove the native oxide and elemental arsenide. Then it is okay, I think. ये okay चल रहा है. Okay, and finally after rinsing it will be dried through a nitrogen gun in order to dry the surface. Now surface passivation of gallium arsenide. I told you I have used ultra thin layer of gallium phosphide. Ultra thin means what? It is actually 1.8 nanometer, very thin. Okay, now ultra thin gallium arsenide passivation layer was deposited again by emulsivity technique, and the precursor I have told you gallium and phosphorus. That is your trimethyl gallium and phosphine. Trimethyl gallium is responsible to supply the gallium and phosphine is responsible to supply the phosphorus, and in that case also hydrogen is as a carrier gas. This hydrogen gas will carry these two compound into the reaction chamber, that will reaction takes place, and finally this gallium phosphide will be deposited onto the gallium arsenide to passivate the surface of gallium arsenide. Next. Now you see fabrication of the memory device. You see again I have deposited this one ZrO2. Okay, what precursor molecule are used here? For zirconia it is zirconium peptide, and for oxygen it is high purity oxygen. Temperature used here 300 degree centigrade. Both two material will go to the again chamber, they will react with each other and it will be deposited onto the oxide. Now for metallization purpose we have used front electrode is your aluminum and back side contact is silver palladium, and diameter of the device is here in the range of 1.9 into 10 to the power minus 3 semi square. Then you see all the devices will be subjected to annealing at 300 degree centigrade for 3 minutes. You see this is the typical structure of the devices. You see I told you this is your gate, metal, oxide and your semiconductor. This is actually your semiconductor material, because very poor native oxide is there. That's why I have passivated the surface with interface passivation layer prior to the deposition of your. Now here two oxide layer is there. Why? You see I told you this is your tunneling ZrO2. Tunneling ZrO2 thickness of the tunneling ZrO2 is in the range of 5 nanometer. See, if you apply the voltage, then electron will surmount the barrier and reach to the indium arsenide quantum dot, because this is control ZrO2. Why control ZrO2 is there? Thickness of the control ZrO2 is in the range of 20 nanometer, much higher than this. Why? In order to suppress the electron tunneling from here to here. If electron goes from here to here, then in that case your leakage current will be higher. So to suppress the leakage current density, I have used here control ZrO2. Again I am telling, when you are applying bias, then electron from gallium arsenide channel will tunnel through this layer. After that it will reach to the indium arsenide quantum dot, and there it will store the charges, and that will actually act as a capacitor. And this is the actual confirmation study. All the layer by layer structure you can see here, cross sectional and HR time image. See gallium arsenide, gallium phosphide, tunnel ZrO2. Okay, this is a very sophisticated tool, and you can and very critical testing will be, because sample preparation is very critical. Okay, you see gallium arsenide, all the corresponding layer, successive layer, individual layer you can see here. Now this is the results and discussion section, where I have used capacitance voltage measurement. You see here, when I swing the voltage from -10 to 10 voltage, you see your memory window will be vary from, okay, actually have this one, the electron charging here is the whole charging responsible for. Actually two types of devices there. This device is actually containing indium quantum dot, and this study is where no quantum dots are present. In order to ensure that whether it is storing charges or not, you see when you swing the voltage from -3 to 3 to -10, 3 to in so many charges there, -3 to 3, 6 to 6. When your sweeping voltage also increases, in this case your memory window also increases. Okay, and here you see no memory window is there, because in this is a control device actually, where no indium phosphide quantum dot is there. Actually no charge storing element is there, so there is no storing the charges. That's why your memory, you did not see any capacitance. Okay, no flat band voltage, your shifting is flat band voltage is there. But in case of this, because here quantum dots are present, that's why your flat band voltage shifting is there when you are sweeping the voltage from -3 to 3, 6 to -6, and 10 to -10. In all the cases you can shift the voltage. Now this is frequency dependent CV characteristics. Why this is important? You see, I told you two things are responsible for storing the charges. One is your indium phosphide quantum dot, and another one is your intercept trap charge density. That can also, so you have to confirm what is the effect of this storing charges, whether it is caused by your quantum dot or interface trap charge density. That's why I have studied the device with frequency dependent CV characteristics. If you vary the frequency, if we vary the frequency, in that case also no flat band voltage shifting is there. This will confirm that, because at high frequency that your trap charge density will not respond. So if you, in case of you vary the frequency, na, that's why it is confirmed that, because your interface trap density will not responsible for that, will not respond very high frequency. So you can see that in that frequency only your memory effect is originated due to your presence of quantum dot, not due to the presence of your interface trap between the gallium arsenide and ZR2 surface. Now this is the JVS characteristics. You, in order to determine the leakage current density, you see very low leakage current is there, that is in the range of 10 to the minus 6 volt, 6 ampere per second square at minus electron, -1. You see this is -1, -1 corresponding to this, so this is actually in the -6 range. Now this is your programming and arranging, this is the actually schematic. Whenever you applying the potential, positive potential here, all the electrons situated in gallium arsenide will tunnel through this tunneling oxide, and finally it will reach to the indium arsenide quantum dot. Here it will store some time, that is actually program state. Whenever you are applying negative potential here, all the stored charges here again swept out into the there. That's why no charge, that is your related to your negative Bayer condition, and that is actually your erasing condition. Now this is your corresponding energy band diagram. All the individual layers you can see here, that is taken from your literature. You can, that value is taken from literature. You can also draw, and that is actually your, why triangular potential barrier is formed here, because this is your gallium arsenide oxide and indium arsenide quantum dot. Here actually, if you calculate, here actually your triangular potential barrier is formed. Rather, I will show you why Falun tunneling takes place in experimentally. Now this is the charge retention capacitance. This is the charge retention capacitance. You see 10 to the power 5 second, you can store the charges at least 87.1. So your device is 10 to the power 5 second means almost your more than 24 hours. Now this is your characteristic study actually, endurance characteristics. You see up to 10 to the power 2 cycle, no such shift is there, almost linear. Okay, no such shift is there, but after 10 to the power 2 very slight. So you can see that your structure is very stable. Okay. you can see if you just calculate the shift now, it is only in the range of 0.1 hectare. That is very negligible. That's why you can for both the cases, for forward cases as well as your reverse cases, okay, for both the sweep. So you can say that your device is very stable. Now this is another strategy where I have varied the size of the quantum dot for memory application. This is the, so I told you already how, because with varying temperature I have varied the size. This is your AFM, and I so told you why size is bigger than this, okay. This is your density. With increasing temperature your side gets bigger while your density gets decreases. Now this is another study. You see, with increasing your with increasing your quantum dot side, you see your memory unit gets decreases. You see, with increasing your store charge density actually proportional to quantum dot diameter. If diameter increases, then this one will be decreases. This will directly related to memory window. So memory again in physical terms, in physical, you can, if your size gets bigger na, then your interparticle distance will be get reduced, okay. In that case what happens, you know, your electron repulsion will be takes place. That's why with greater the size your charge storage will be less. Again, this is the frequency dependent. Why frequency dependent? I told you, in order to ensure whether it is caused due to your quantum dot or it is due to your surface charge density, that is actually your confirmatory test. This will confirm that because of your presence of your quantum dot, this actually things are happen. If, okay, because here no flat band voltage shifting is there in all the cases. Even if you vary the frequency from 50 kilohertz to 1 megahertz, in all the cases same characteristics happen. That will confirm that your storing charge is happening due to the presence of quantum dot, not due to the presence of your interface trap charge density. Again, this is the your excess capacitance, this is your retention characteristics, how long your charge will be stored here. In all the cases, you see, in all the cases your charge will be at least your 87.1, okay. Now I have used all the three structure. All three structure I have used. Why? Because of the theoretically conduction model to determine the conduction model in all the devices. First of all, here no passivation layer is there, and second case is gallium arsenide passivation layer is there. In third cases, along with this only extra layer is your quantum dot. In all devices, how your electron transport is taking place, that is actually main study here. You see, here no passivation layer is there, here passivation layer is there, and here along with passivation layer your quantum dot is present. How electron charge transport is taking place, that I have studied here. In all the corresponding your device structure is actually cross sectional TEM, HR TEM or rather TEM you can say, all the individual stack by stack layer you can see. Again you see, this is your, you see where when you passivate the surface device with gallium phosphide passivation layer, in that case you see your leakage current will, in this case leakage current will be low, and without passivation layer your leakage current will be higher. See, when you passivate the surface with gallium, in that case your interface trap charge density will be lower, and when without passivation layer, then your interface trap charge density will, that will lead to your high leakage current density. That's why without gallium phosphide passivation layer you can get your higher leakage current density, and when you passivate the surface with gallium phosphide passivation layer, in this case your leakage current will be lower. This is another study to confirm what kind of electron transport actually takes place. Okay, you see here from 0.5 to 2.44 volt, this is actually Poulet-Frankel. So many conduction model is there. Poulet-Frankel, Fowler model tunneling, and thermoionic emission. Okay, so actually what kind of electron conduction is taking place, to ensure that one, for confirmation test I have also systematically study your current voltage characteristics. You see from 0.5 to 2.5, if you plot this device from this one, this equation by, you see from 0.5 to, so you can very linear ranges obtained you can, okay. So in this region from 0.5 to your 2, you can say that in these devices your carrier transport basically followed pole Frankel emission. And in case of your passivated devices, you see, if you plot these devices according to Fowler-Nodem equation, you will get this type of characteristics, and which is also getting linear. So from you can see that from 1 to 4, okay, uh, uh, you can determine that, you can confirm that your device is followed Fowler-Nodem tunneling, because in this region, in this to this voltage region, current is followed Fowler-Nodem equation. Now this is your devices where intimate quantum dots are present. This is your leakage current, current voltage characteristics, and this is your corresponding IV log JV. As per your Fowler-Nodem tunneling, very sharp decay is there. Here from 0.5 to 1.5, you can see it also follows your Fowler-Nodem tunneling mechanism. So this is the conclusion actually. What is the conclusion? We have fabricated the, first of all we have growth the indium arsenide quantum dot on bare gallium arsenide substrate as well as your ZrO2 layer. Second one, we have growth the indium arsenide quantum dot comparatively below temperature from 380 degree centigrade to 450 degree centigrade. And you can see the maximum memory window, the large memory capacitance is found is that 6.83, and your very low leakage current density in the range of 10 to the minus 6 ampere per second, and retention characteristics at least your 87%, and even after 10 to the 5 second. I have also studied the size effect again as well as your leakage current density and the quantum sun model, where in case of passivated devices it will be followed your Pule-Frankel, and where quantum dots are present it will be followed by your it will follow Fowler-Nodem tunneling mechanism. Now this is completely another research work which I am currently undertaking in Sri Pilani. This is actually graphene based devices. This is actually synthesis of graphene. You know, this is all related to your material processing, how we have fabricated your preparation of graphene. This is actually graphite electrode, graphite sheet is there, it will be dipped into the solution, FeSO4 and Di water is there, and finally if you apply the voltage between the two electrodes, then graphite sheet will be converted into graphite flakes. That graphite flake will be dipped into the black tea solution. When you rinse the ultrasonication, when you finally rinse it into the ultrasonication more than 5 hours, then it will be converted into the liquid graphene. And now for the fabrication of devices, because it is actually related to your flexible, okay, so that's why we have also, first of all we have fabricated the flexible substrate as well. For flexible substrate preparation, we are using silicon elastomer as a base material, as well as silicon elastomer as a curing agent in the range of 10:1, and finally it will be deposited into the, this is actually silicon board, okay, wafer, silicon wafer, we have deposited the material on that, and finally it will be drop casted onto the wafer, followed by baking. Baking means temperature processing, nothing else, at 80 degree centigrade for 45 minutes. After that it will be peel off from the surface, and finally you can get this kind of thing. Okay, when you peel off this one, you will find a circular shape, because silicon is circular shape here, you can get this kind of substrate. Now this is actually why you are using, because they actually confirm the flexible, bendable, rollable nature and stretchable nature as well. First of all, initially it was that if you stretch here, you can stretch up to 6 or beyond that as well. Now whether your graphene is formed or other material is formed, this is again your Raman experiment actually. You see all the characteristics picture happening, D band, G band and 2D band. This confirms the formation of graphene. Why D band arise? This is responsible for the defect state present in the graphene. G band actually your carbon-carbon stretching, rather you can say is the vibration of the sp2 hybridized carbon atom, and 2D band is responsible for your stacking of carbon layers, and this is the corresponding FEGM images of the fabricated graphene as well as the transferred graphene onto the PDMS substrate, because for the fabrication of devices your synthesized graphene will be finally transferred onto the PDMS substrate. Now you can see this is the another results where your graphene based flexible devices will be used to monitor the human pulse. Whenever this is actually pulse signal, whenever you are wrap up your device into your human wrist, see your device is there, you can also capable to detect the human signal, human pulse signal as well. You see, whenever you are keeping this your sensor here, you see your gradual change of resistance is happening in all the cases. This is actually fabricated device on PDMS substrate. Here you have used your PET, polyethylene terephthalate. This is actually your polyimide substrate, and here it is actually graphene on carbon fiber. In all the cases you see graphene is active material which will detect the your human pulse, because whenever human pulse is happening here, it will detect the human pulse. In all the cases your device resistance will get changed. This is another study where we have synthesized so many your three kinds of metallic, three kinds of graphene based nanocomposites are there: silver nanoparticle, carbon nanotube, PDMS, and in all the cases we have determined that, studied that which material is suitable for your flexible application. Later I will show you. This is all related to your material processing, nothing else. You see, again another study is there, all the cases, because all three are your, in all the cases D, G and 2D band is happen to arises. So this again confirms that your material is basically carbon nanotube, graphene, and your here also GNPO is there. This is basically graphene nanoplatelets. So all the compounds is contains actually carbon molecule, that is actually graphene. And again here you see we have tested the device which your, this is GF means here gauge factor. Whenever you this is actually stage when tensile strain is you applying from this to this, your device relative resistance is changing, that is actually determining. Okay, this gauge factor is actually sensitivity. Okay, in this case 188, in this case this one and this one. So you can see from this plot the maximum gauge factor is we obtained is 221. So this device is actually getting better results. Now for breathing analysis, this is actually human breathing analysis. You see the sensor is very much stable. Whenever this sensor is mounted on human mouth, whenever deep breathing you are, when you deep breathing and during normal breathing, it can also changes your relative resistance changes is happening with respect to time. Okay, in all the cases, this is your silver nanoparticle multiple PDMS composite. In this case also, your relative changes resistance is happening. When deep breathing, then change is relatively higher, resistance change is relatively higher, and when normal breathing is there, getting low. In all the cases you see, in this case also. So this actually confirms that your device is sensing. Your graphene layer actually device is formed, and graphene layer is actually sensing your human breathing. And now for analysis of response and recovery time, it is actually from the previous data we have taken this one. In that case you see graph is from, this is actually response. Whenever this is response, again here you see from this to this getting recording decreasing. Okay, and from this turn again device is getting recovered actually. So if you calculate this one, this value to this value, it is actually 152 millisecond in all the cases. Okay, you see response time is quite low where silver nanoparticle, GNP and PDMS. In this case your response time is quite lower. Okay, and here 130. So you can see that the device containing silver nanoparticle, GNP and PDMS substrate is superior rather than these two. Now this is another study where we have fabricated flexible solar cell using so many polymers actually. Here also comparative study is there using your MHPP and P.PSS on PT substrate. You see all the devices are actually same, but in these devices we are using two types of polymer. One is your MHPPP, another one is a P.PSS. This is actually whole transport layer and this is your photoactive layer. This is actually capturing the photon and it is actually responsible for transport the carrier. So in this case we have obtained very good result. So device D actually superior in comparison to other device. You see from device D your fill factor and efficiency is quite higher rather than other three. This is another solar cell study where rather than using polymer substrate we have used cadmium sulfide as a photoactive element. This cadmium sulfide is also as a active material. You can see here fill factor is 56% and efficiency is very low. Even your photocurrent, your one sun during one sun examination, it also exhibits your very low leakage current VOC, this one, and efficiency in the range of 10 to the power -3 or -4 range. So this also confirms that it is also can be applied as a solar cell material, but because value is very low, so several optimization will be needed in this study. Now this is another study, this is actually simulation study where photonic crystal based structure will be there. It is actually SOI. SOI means silicon on insulator. This is actually silicon. This one is SiO2. This one actually device layer. This is actually silicon. Silicon oxide, silicon. So the device is patterned in such a way so that your hexagonal lattice is formed with circular lattice. Actually, your funda is that whenever you are applying some analyte or water or any other solvent to the surface, your refractive index of the surface will get changed. That change in refractive index will be responsible to shift in wavelength. You see, whenever your lattice constant will vary, your wavelength also vary. The latter study, this is your variation of hole diameter with respect to wavelength. When you vary the hole diameter from this one to this, your wavelength also varies. But our intention is to get the photonic band gap region from 400 to 800 or in the visible region. So you can see with that much of lattice constant A equal to 200 degree centigrade, we have actually obtained the photonic band gap. So that's why we have taken A equal to A lattice constant, this is 200 nanometer. So this is actually optimal structure where the lattice constant is 200 nanometer, hole diameter is 120 nanometer, you see, and this is the shift in wavelength. I told you whenever you change the refractive index from 1 to 1.2, your wavelength shifting also takes place. And this is actually sensitivity. If you calculate the sensitivity from here to here, okay, your sensitivity you will obtain is 91 nanometer per refractive index unit. So this is actually your photonic crystal structure. You can see here several color diffraction pattern is observed, and this is the individual component. Actually, our main focus, final focus is that it should be your smartphone integrated module. For smartphone integrated module, we have actually optical module. We have designed so many collimator lens, camera, polarizer, and cylindrical lens. We have this is actually photonic crystal. Whenever light is coming from this side to this side, actually this photonic pattern is actually visible. Now this is another study where I have designed your LED structure actually. All basically based on your simulation and design. This is not experimental. All the parameters are there. We have using this is simulated software. Okay, all the individual layer you can see. Sapphire substrate is there. All the individual layers, the composition and your density also we have. This is for UVC region. In order to achieve the UVC, we have device structure will be like this. You see UVC 266 nanometer is lies in the UVC region. This is your internal quantum efficiency, your 25%. This is turn on voltage, device turn on voltage is your 5.2. Actually from this your device is getting turned on, and if you output power calculation, this is the output power study using both electrode. What is that electrode? One electrode is your finger type electrode and another one is your circular type electrode. You see, using your circular type electrode, you are getting quite higher your power efficiency. Output power is 14 milliwatt at 50 milliampere current, and in this case 4.9 milliwatt at 100 milliampere current. And again another study is there. This is UVB LED because that is our project actually on just completed. Another study UVB region. Again like this one, all the individual structures you have to 5 quantum well. Okay, and again you have parameter you have taken what is the mobility hole, what the your basic parameter in the software you have to set. All the parameters I have taken this one. You see in the result UVB 295 nanometer. You can see from 280 to 320 belongs to your UVB region, and all the internal quantum efficiency turn on voltage In this case, your internal consistency is 85, which is far better than the previous one. And output power for both the cases 11 milliwatt, and in this case 2030. For circular electrode, we are actually getting very good result. Now this is another study where we have used a copper strip for heat sink material. Actually on that copper strip we are mounted your LED, actually that UV LED. This is the actually design of the copper strip. On the individual LED will be situated here in the next slide. I am showing this one. See, all the individual LED is there. Okay, this is actually your copper. This is your star packages, and it is subjected to fix it in using your silver epoxy. And in the next slide, you see all the LEDs working well with apply. This is actually series connection, and all the three strips are in parallel. Whenever you are applying 25 voltage, your all the LED is glowing. And finally, I am concluding this one. This is my list of publication. Next. Next. This is my list of publication. Few after joining in Siri. Next. These 3 book chapters also there. Next. This is the all the conferences I have attended, published. Finally, thank you for giving me an opportunity. And if you have any question, then I will be happy to answer.
I mean, I don't know about gallium, sir, but how much is that gallium nitride or gallium arsenide technology contributing to improvement of reverse recovery times?
Reverse recovery time of what?
I mean, to come from whether to on state or to off state.
See, gallium nitride is completely another set of material. In case of, because that study I did not undertaken in case of gallium nitride. For gallium nitride, I have shown your LED actually. For light emitting devices, I have undertaken gallium arsenide. Okay, and in that case, one main thing is that if you consider the band diagram, na, your electron band gap in case of gallium is 1.43, and in that case, your gallium nitride 3.4, something like that. So very high. So in that case, it will be very difficult to control.
Thank you, sir, for your insightful address. Now I call upon our FDP coordinators to present a memento as a token of gratitude to Dr. Masiul Islam. Thank you, everyone. Now I invite everyone for a refreshing tea break.